All right, EET112 Lab 3. We're moving on to part B now. And the first thing to do is assemble the circuit in figure 15. I still got the scope. It's still exactly the way it was at the end of part A. So now what I want to do is let the scope run. And I'm going to, just for the moment, I'm going to get rid of the cursors. And I'm going to turn on channel 2. And channel 2, so DC coupling, yes. Full bandwidth limit, let's go to 20 meg. Probe needs to be at 10x. All right, and your probe 2, the little red switch, should also be at 10x. All right, now I'm going to turn on the function generator. So we should have, oops, it was already on. Great. Gotta wait for it to boot up now. It had been on so long that the screen went blank, so I thought it was off. So we want to set this to 10 volts peak to peak, frequency of 1 kilohertz. So amplitude 10 volts peak to peak with an offset voltage of 5 volts, 5 volt DC, and turn it on. So there it is. Well, our horizontal time base needs to be adjusted. So let's turn that at least to somewhere in the millisecond region. Oops, wrong way. Oh, I've got it on sine wave. And the trigger's way down here. So I'm going to push this button to put it in the middle. I'm going to go to square wave. Square. Okay, there's the square wave. All right. So let's put the channel 2 also at 2 volts per division. 2. And we're going to turn its vertical position down to that minus 6.0 to get the bottom of the waveform to be essentially at ground. Wrong way, Feldman. There we go. And let's move the horizontal something like this for now. So what you see here is the square wave. Of course, it's got a sharp edge. This is like turning on the switch to 10 volts. And then the cap charges up in the purple. So we've got the channel 2 of the scope is monitoring the cap voltage. So now, just like before, we want to measure the time constant. So let's go a little further with the horizontal. Spread this out nicely, and then use the this positioning knob to move it over to the left. Okay, that's pretty good. And then we'll measure tau just like we did with the 100 microfarad cap, only this time we have a 10 nanofarad cap. So turn the cursors back on. And again, let's put X1 right at the start there, right on that vertical edge. Looks good. Now Y1, if I hadn't, it's still exactly where it was before, so I don't even need to move, Y2 or Y1. Y1 is at 0. Y2 is at, 63.2% of 10 volts. So all I need to do is move X2 to where it intersects the purple waveform there. So let's go to X2. And we'll move it over. Just about there. Okay, so our time constant in this case is going to be delta x, the time from here to there. That's the time it takes to charge up to 63.2%, 49.8 microseconds. So just see if that makes sense. My calculator here, 48.9 microseconds, divide by 4.7 k ohms. Now you would divide by whatever your measured resistor value is. And I get about 10.4 nanofarads. So pretty accurate here. So that's the charging up. And then now we want to measure the discharge time. Oh, actually, you're supposed to measure the other levels, which is one thing I didn't do in the first part. So for the other percentages, you'll just move the Y2 up to those other various levels. And I can't remember what they are off the top of my head now. So, but just as an example, if you wanted to move Y2 up, then you would select it and then move it up to the next level, whatever that happens to be. And then you would move your X over to the intersection, and you would know what delta X is. And that's the time it takes to go to, for example, 2 times tau. All right, hopefully that's clear. And you would do that for I think you got to do 1 tau, 2, 3, 4, and 5 tau, and put those numbers in your table. Okay, and then for the discharge, what we do here is we're just going to, well, all you need to do is change the slope of the trigger. So instead of triggering on channel 1 rising edge, we're going to trigger on channel 1 falling edge. So let's put, let's see, trigger menu. So slope rising, we want slope falling. So I went to the trigger menu and chose slope falling. And so now we're going to measure the discharge times. Okay, so for the discharge times, it's very similar. We want to measure how long it takes to get from 10 down 63% of that 10 volts there. So that would be, 10 minus 6.32, which is, well, actually, we can just use the delta Y to get that. So our delta X, or our X1 is right where we need it to be. So let's move Y2 up to the top. So cursor's back on, Y2, let's move it up to 10 volts. Say Y2, 10 volts, you can see it right there. And now we're going to choose Y1. Y1, and we'll put Y1. We want to put this so that delta Y is 6.32. Right there. So you can see delta Y is 6.32 volts. So we go from 10 down to there. That's a drop of 6.32 volts. And you notice that Y1 is at 3.68 volts, which probably corresponds to a number in your table there. So now now we will adjust x2 to intersect right there. Well, it already pretty much is already intersected there, because as you would expect, it's going to take the same amount of time to discharge as it does to charge. So once again, I've got 49.8 microseconds. And then, as before, you'll need to move this this Y1 level down to the next level, or 2 tau, whatever that voltage happens to be. So you'll move it. Let's see, we already got it on Y1, yep. So you would move it down to the next level. I'm sorry, I can't remember what that is off the top. But say it's right there, then you would move X2 over and measure that time from here over to there. All right. So that's pretty much it for part B, except for doing some of the calculations, which I'll show you in a third video. Let me know if you have any questions about that.